I hope you will be able to read properly. So let's write it. Epsilon naught in L plus 1, and then dl a to the minus L plus 1 is equal to epsilon in minus L AL A to the L minus 1. Did you find any issues with this? And this is for L greater than 1. This was our equation 4. Okay. So let's move on. That from equation 1, A naught is equal to B naught A to the power minus 1, and this would imply that our A naught is equal to 0. How? Using equation 1 again. Yes?
The other one is supposed to be true.
Pardon?
Yes, sir. Yes, it was big M plus A.
The components in the equation, huh? Let me see how it is. Okay, so we got where are you talking about the 2?
Index of
Here. This one. Is that okay? We can do that. So using equation 1, A1 will be equal to B1 and then A to the minus 3. This becomes our equation 5. Substituting into equation 3, substituting in equation 3 yields, so I got epsilon naught in E naught plus 2A1 is equal to epsilon in E naught minus A1. This would imply that if I cut out the expansion, I will get that 2 epsilon naught plus epsilon in A1 would equal to epsilon minus epsilon naught in E naught. And further, this can be able to give me A1 being the same as epsilon minus epsilon naught over 2 epsilon naught plus epsilon in E naught. I call this one equation 6. Equation 5 gives, so I have that B1 is equal to, that was our equation 5, is equal to B1 A to the power minus 3, and that would imply that our B1 would equal to epsilon minus epsilon naught over 2 epsilon naught plus epsilon in E naught, and then we have our A cubed. So I should have gone with A cubed E naught. So this is A cubed E naught. And substitute equation 1 in equation 4, and this becomes our equation 7. Substituting yes. Pardon? I think this one should be A1 here. This should be A. This should be positive, and then this should be A1. By making B1 the subject, this one comes down here, and when we raise it up, the index becomes positive. So substituting the equation 1 into equation 4 yields epsilon naught into L plus 1 BL A the minus L plus 2 is equal to epsilon into minus L dl at the minus 2L plus 1 A to the into L minus 1. And this can be reduced into epsilon naught into L plus 1 into BL, and all that into H power minus L plus 2, and this should be equal to epsilon into minus L BL. I'm not really trying to explain because this is just, algebraic gymnastics. And this would be the same as A to L plus 2. And this should be able to give us thus that our epsilon naught into L plus 1 plus epsilon 1, we chose epsilon instead of epsilon 1. So in epsilon L, BL is equal to 0 for when L is greater than 1. And since epsilon naught is greater than 0, and also, of course, we know epsilon naught is how much? Is a positive value. So these two permittivities are above 1. They are positive numbers. So if that is the case, this would imply that we conclude that BL is equal to 0 for L greater than 1. So this would imply that all the ALs would be equal to 0 for when L is greater than 0. Now the final solutions for the potential are, so we substituted, we have V exterior R theta being the same as V naught plus the epsilon minus epsilon naught over 2 plus epsilon naught, the epsilon, 2 epsilon plus epsilon, which I've rearranged just to make sure the epsilons are occupying, comparable spaces. E naught A cubed, the other one. And then we have cos theta over R squared. And our V immediate, the V immediate other theta would be the same as V naught plus epsilon minus epsilon naught over epsilon plus 2 epsilon naught, and then you have E naught R cos theta. Since E naught R cos theta equals to minus V naught, because we said V naught is the same as or values. You remember when we looked for potential along the Z in terms of the PL cos theta? I mean, by getting the component of this potential along the Z, by saying from E is equal to minus grad V. So our E will be equal to that. Okay. So we get our V immediate R theta being the same as minus 1 plus epsilon minus epsilon naught over epsilon plus 2 epsilon naught E naught R cos theta. And this would be the same as minus, we multiply here and then add, so it will be minus 3 epsilon naught, because this will be minus 2 epsilon naught goes with that. This is minus epsilon, cancels out. Over the denominator remains epsilon naught. And then we have our E naught R cos. And then therefore our V in area R theta, we are having no phi because phi is chopped off due to azimuthal symmetry. So this would be minus 3 epsilon naught over epsilon plus 2 epsilon naught. And then we have E naught Z. You know Z is the R cos there. And we could bracket this if we want. You could have this as the potential. We notice that immediate field, the immediate field is constant and uniform. So this field is constant and uniform in the immediate, because Z is just showing us along where it is going, but this is a constant permittivity of the electric sphere. The permittivity in the medium where the sphere is lying is constant, so that's why we are saying it is constant and uniform. So if we notice that, so E immediate Z component would be the same as minus Kali V by Kali immediate by Kali Z. And this should be equal to give us, if you do it in your free time, 3 epsilon naught over epsilon plus 2 epsilon naught E naught. From D, the electric displacement equal to the epsilon multiplied by electric field intensity. I think I'll be doing this all the time because it feels nice to find no dust going astray at all. Remember that may also remain smart. So the inertia displacement, electric displacement vector is the same as the permittivity of the inertia of our dielectric multiplied by the inertia electric field. So the inertia would equal to 3 epsilon naught over epsilon plus 2 epsilon naught E naught. So which is equal to 3 epsilon over epsilon plus 2 epsilon. So if I take the epsilon naught outside and I combine epsilon naught and E naught, then they will give me D naught. So I have this as D naught, where D naught is equal to epsilon naught E naught. And so if we have the permittivity of the dielectric being greater than the permittivity of the outside, that is if the dielectric is more permittive to the electric field in which it is residing, then we would have that the E inertia, the electric field inside, would be less than E naught. If we have this being big, we are having this only 3 times divided by twice the epsilon naught, and you would have the inertia field being lower than the outside. But we know that the electric displacement inside the dielectric is greater than, so D inertia is greater than D exterior. Okay, so we have almost done a few things about this example comfortably. Are there any queries? So we've now looked at Cartesian coordinates. We've looked at spherical coordinates, and then now we are going to cylindrical. So we want to see if we have a simple potential problem, and we want to use Laplace's equation to solve this problem. How do we tackle, or how do we handle the idea of using cylindrical coordinates? I'll start by, but if you can visit where you'll be able to see the demos there. So I'm going to make a virtual cylinder. So this is our cylinder, and our cylinder, if we make it stand, and we are taking this cylinder to be along the axis of the cylinder to be the z-axis. So what I'm talking about is that we are having a cylinder which looks as beautiful as this. So if I take this to be the center of the cross-sectional area, and I take this one to be our Z, and then I take along the cross-sectional area, like the cover of a tin. So I have my X here, and I have the Y here. Of course, the Z continues down here. In the diagram, what you'll be seeing is that if I am going to take any point on the cylinder, that is on the sides of the cylinder, if I am to take any point and I want to know the coordinates of that point, so any point P, it can be defined by R can be defined by phi and z. In some textbooks, you'll find this one being used as rho. In our own book, which is the e-book which we are using, Griff, you'll find that he's using S. The reason is that not to confuse it with the coordinates, whereby when you talk of the x for the spherical, and you have y and the z, for any point on the surface of this sphere, that point there is being specified by the distance from the center, which is r, how much that projection, that line from the center, the angle is making with the z, the zenith, which is our theta, and how much you can go around on these points, different points on this sphere, and this angle here. For any point, its projection here on this sphere, this will be our phi. So you'll be having these coordinates being phi. So in order to not confuse these two, because for these coordinates, actually the kind of arrow we are talking about is that if we are taking this point to be somewhere around here, if this is the projection, this will be our phi. And then in the Muele demo, it's that red thing which turns around like this, a plane. It sweeps through the phi. But the r is the perpendicular distance, this distance, which we are, this perpendicular distance is the r. That's why some people choose to call it rho or s. And then the distance from the bottom here, from this point, from the projection down of this r here, up to the top is what we are calling the z, and the phi is the angle you sweep through as you try to make the cylinder complete. Okay? So now we can go to the cylindrical, which is our, we shall still use r, but at the back of our mind we know this is the r, being the distance from the z to the side of the cylinder, where the point where we are taking our point within the space around the cylinder. And then we know that our phi is the angle swept across, either the cross-sectional area, and then the z is the distance. If you were pouring your liquid in a cylinder, that height of the meniscus, how it rises, is what we have as the z. So here we have the r, theta phi, here we have the x, y. So Laplace's equation, Laplace's equation in cylindrical coordinates. I should have left this part for you to do, but let me see how much I can do for you. So we use our Laplacian equation, where the Laplacian in cylindrical coordinates, del squared v is equal to 1 over r kali by kali r inu r kali v by kali r. And then I have plus 1 over r squared kali squared v by kali phi squared, then plus the kali squared v by kali z squared is equal to 0. We can call this one equation 1. And of course, if we are talking of our potential being, it will be, our v will be varying with the cylindrical coordinates, which is the same as v r phi z. Diagrammatically, we can represent, I can draw now officially our cylindrical coordinates. This is our cylinder. So I will give it a short chassis. And but I think further, after talking of Andre, he deserves something. So if he continues eating cassava on you, so 10% of the total cassava, you will continue clapping for others. Even when you go, when Subir does something, then you clap, thank you, then he goes home with a bag of money. So we have, I said the rules, 10%. So this is X, this is Y, and we have our Z. So if we had any point, please, if we had any point on the sides of this cylinder, and we have that point around here, the R, but the R, so this point here, if it projects on this plane, which is the cross-sectional plane, and I can put this up to there. So this is our R, and this is our phi, and this is our Z, but this same R is the same as the R if we are moving from, so this is also R. That's how we interpret the cylindrical coordinates. So C muere for a clear diagram, not explanation, but a clear diagram. The solution by separation of variables, requires to put, I will introduce the other capitals. So what would be the capital of phi? No cassava. This one is equal to, how do you write capital phi? We know that this is phi, or what I'm now calling phi. What is its capital? Capital phi or phi would be what? You say it is like, so what is that? How is it pronounced? I have understood it. I have understood that you are saying I do this. So what is it called? Psi. Did you do quantum mechanics? You didn't do quantum mechanics?
We did quantum mechanics.
So V R phi Z would be equal to capital R, psi, phi, and Z. So I don't know whether we should just, I'm not going to put a slash on the capital Z. So this would be our equation 2. Equation 1 was the Laplacian operator on acting on V giving us that, and then we get our variables. So we note that the L is equal to the R cap or roof plus R the phi roof plus the Z roof, and grad V is equal to Kali V by Kali R plus 1 over R Kali V by Kali phi plus Kali V by Kali Z. This is to help us when we come to the point when we're looking for the electric field intensity, we shall invoke this kind of expression. And when we are looking for somewhere where we are using the L, we need to know how it is given. But these all will be given on identities in in the tests and in the final exams. And the tau, the volume, is the same as R dr phi dz. So now let's do our business. So using equation 2, if we now substitute this equation into the Laplacian, then we shall have that using equation 2 in 1, we would have that 1 over small r capital R d dr into r the capital R, the small r, plus 1 over r squared psi, the squared psi, the phi squared, plus 1 over z capital, the squared capital Z, the small z squared is equal to, and this is our equation 3. Let's set the z equation, that is 1 over z, the squared z capital, the small z squared equal to a constant k squared, and call this one equation 4. Once we set that, this would imply that we get a solution of z being the same as a exponential kz plus b exponential minus kz. Or we can write it invoking the hyperbolic functions, that z would be the same as a sum kz plus b cosh k. How do we pronounce this? It's sin. So Laplace's equation becomes Laplace's equation becomes r over capital R dr into r the capital R, the small r, plus 1 over r squared psi, the squared psi, the phi squared, plus the z part, which we said should be k squared, is equal to 0. Multiply throughout by r squared, multiply throughout by r squared yields, so I can say multiplying throughout by r squared yields r over, oops, what did I do? Say Laplace's equation becomes, this is 1 over small r. Let me validate this first. That is okay and that is okay. So when we multiply by r squared, we remain with r on top, capital R on the bottom, d dr into r dr small plus 1 over psi, because the r squared goes, the squared psi, phi squared, plus k squared is equal to 0. Separating out psi gives 1 over psi, the squared psi, the phi squared is equal to minus nu squared, this one. There is this, there is this, and there is that. Yes? I think on the last part we have another squared, k squared r squared. It is always nice to see that you are following. So that is nu squared, and we get our equation 5. Our equation 4 was for the set part of the z. So now I can say that this would imply that the solution of this equation in psi would be the same as psi phi is equal to a1 exponential minus I r phi plus b1 exponential minus it should be minus nu dot r. This is nu, like this nu. This would be minus nu phi. I think 1 is positive. This should be positive, I guess. I will check properly later. But you can also write this one in terms of the trigonometrical ratios. Psi phi is the same as C1 cos, sine nu. So if this is plus, then that means it will be sine nu phi, then plus D1 cos nu. The nu is like a V, but which is elongated at the bottom. It's like you make it so it's like a V, but not a V. The computers know it, yes? No, they are just because we are now using this expression, we are choosing another set of constants, C1 and D1. Probably. Let's change hearts. Doesn't matter. C1 can equal to A1 and B1 can equal to B1. Finally, R over R, ddr, nu R dr plus k squared R squared minus nu squared is equal to 0. Or we can write it as R ddr nu R dr plus k squared R squared minus nu squared into R is equal to 0. And this should be our equation 6. And now we will that introduce an x equal to k r, noting that when we differentiate both sides, we would have d dx is equal to k dd dr. So this would imply that d dr would equal to 1 over k ddx. And if we do this in equation 6, then we shall say that so the equation 6, let me pronounce it the way. The equation 6 becomes x squared, d squared r, dx squared plus x dr dx plus k squared r squared minus nu squared e nu r is equal to 0. And we have our seventh equation. And then we say that a general expression of equation 7 is x squared y squared plus xy first differential plus x squared minus n squared y is equal to 0. That is our eighth equation, where n is a constant, and it's called the order. It's called the order of the Bessel functions. And these functions were an equation A is called the Bessel equation. The Bessel equation. Now you can recall very well from mathematical physics. And its solutions, the solutions to 8, and its solutions are known as Bessel functions. Bessel functions. And they have a general solution. They have a general solution. I can't make the blackboard look nice and then I just run away to leave it to other people to make it better. I have to realize it. So a more general solution is given by yx is equal to a jnx plus b jn minus jnx, where a and b, when b are arbitrary constants, and these arbitrary constants can be gotten by noting that, or we need to note that unanonymous circumstances, we got that Jnx is equal to minus 1 Jnx, and Jnx is equal to summation k equal to 0 to infinity minus 1 to the k 1 over k factorial into n plus k factorial x over 2 to the 2k plus n. This is how we get the Jn's. We now consider the case of V equal to V. And we consider the case where we get the potential value as the polar coordinates are theta. That means when you take a smooth symmetry, then we would use the expression for the in cylindrical coordinates, which is that 1 over r ddr into r dv dr plus 1 over r squared squared b phi squared equals to 0. And we take this one to be our equation 1. We seek for a solution of the form. We seek for a solution of the form where we say that V would be given by R and then theta. And then we shall say that equation 1 becomes, if we substitute in, equation 1 becomes, I said no, let it should always sit together because you are good at remembering. At least for next time. So R over capital R dr inu R dr capital the small r plus 1 over psi. Oh, sorry, this was not. We are dealing with something I messed up. These cylindrical coordinates, we are dealing with r phi z. So this one here is phi naught theta. And then here when we take the capital phi, it becomes psi phi. So I'm sorry about that. So we got our variation of potential being valid as r and phi. So if we only took the bottom of the cylinder, this is our cylinder. And if we just took the cross-sectional part of the cylinder by eliminating the z, so like we don't care how long it is, because properties will be the same if we are moving along the cylinder. So no matter how long it gets, it wouldn't matter. So that would be, we are on 1 over psi. 1 over psi, the squared psi, phi squared will equal to 0. And then that comes to the, looking at these two differential equations, that r over r dr inu r the capital R the small r is equal to k squared. We can take this on P equation 2, and when we take the psi phi equation, which we can also say Angela equation, then we get 1 over psi the squared psi phi squared. If they are to be linearly independent, then they should be equal to minus k squared. This is our equation 3. And then we get that we consider the radial equation. We consider the radial equation. And this radial equation is the one concerning the radius, and this is equation 2. Then we got r squared, the squared capital R, the small r squared plus r, the capital R, the small r, is equal to k squared positive capital R, and this gives equation 4. There are a couple of scenarios, two scenarios. Scenario 1, or call it case 1, if the constant is equal to 0, then the equation 1 becomes r over capital R ddr, equation this one here, is equal to r dr will equal to 0. Is it equation 1 or equation 2? This is equation 2, not equation 1. We are looking at the radial equation here that when k is equal to 0, then we have r of this, ddr of this equals 0. And when that happens, we can also multiply throughout by r and divide throughout by small r. And then we come up with something a little bit reduced. So on integrating, we get our, of course, this have gone to 0, it would have gone to 0, you remain with ddr in smaller capital R, I mean the capital R, the small r equals 0, this one's, oh sorry, this remains. This is the instruction of differentiation. If you integrate it, it means you would have differentiated, to get a 0 you should have integrated, I mean differentiated a constant. So you get a constant a, and then this one will go away. And then when you try to make this, rearrange it, you divide by r both sides. Then you again do the integrating again. Then you get something. So on integrating, we have r dr, the small r is equal to a, and this a, where a is a constant, and this would imply that our ddr small r will equal to the ratio constant over a. Integrating the second time, integrating again, will yield that our r, small r, is equal to a natural log of r, and then plus b, where b is a constant of integration as well, where b is a constant of integration. Such that when k is equal to 0, as the case 1 we are taking, then equation 3 becomes equation 3 is the angular component. Equation 3 becomes the squared side, of course. You multiply by side throughout again, I guess squared psi squared is equal to psi k squared. So this becomes that d squared psi phi squared will be equal to 0. So with the solution of the form, psi phi equal to c phi plus d, where c d are constants, Thus we can recognize that our potential VR theta and VR phi is a combination of these two solutions, which is the solution due here for the RR, that is A being R plus B, and then we multiply it by our psi phi, which we just got in here, and that is C phi plus D. This is our potential due to a cylindrical configuration of charge resulted into a potential, and we can call now this one equation 5. Questions? If there are no questions, we can take case 2 when the constant is not equal to 0. So case 2 is when the constant k is not equal to 0. So the radial equation, if we can start with the radial equation, 2 becomes, we have it as R over capital R, the small r in small r, the capital R, the small r, is equal to k squared. So k squared, k now is not equal to 0, so it's going to be persistent, which has a solution. This will have a solution which has a solution of the form RR is equal to AK R to the K plus BK R to the minus K. So which has the solution that we get a solution for the when K is equal to when K is not equal to 0. And then we call this one equation 6. So equation 3 becomes, that is the angular equation. The angular equation becomes, it was 1 over psi, the squared psi, the phi squared, equal to minus k squared. So it will now become the squared psi, the phi squared is equal to minus k squared psi, for which the solution is psi phi equal to b exponential minus plus I k phi. Of course, where g is a constant, and k is an integer, Or we can have the solution being the same as sin phi being the same as ck. We want to see the total eclipse. So now you know why I had to get a phone call when I was teaching. Now you realize why. So we've said that or we can have this as ck cos k phi plus dk sin k phi. And let's call this one equation 7. So that's the general solution becomes the product of the two. Thus the general solution becomes V out of phi is equal to the part of RR, which is AK RK plus BK R minus K inu. We choose either the other one. We can either choose this or choose this one. Here, depending on how you want or which one will help you to do this comfortably. So I will choose to use the next one, and that is ck cos k phi plus dk sin k phi. And this is our equation 8. The constants AK, BK, CK, and DK are found by applying. Should I put cassava? Dash the problem. I've never seen a lady so anxious. So what is the answer there? I don't give ladies money, so you work for free. So what is the feeling? Boundary condition. I don't give ladies money, so I'm sorry. Although it is right. Pardon? I didn't put a pardon. You want a cassava? Yes. Why? Did I put the cassava in the same? They also say so we successfully now seen the cases of Cartesian case 2 we have spherical. Case 3 we have now finished looking at cylindrical. And we now have an idea how we can look for the potential in these configurations. Now next we need to do an example, and this example will help us find a bit. And also after this example we shall do an example on the Bessel, using the Bessel's equation. If we have a region where the charge density is not equal to 0. Any questions really? So example, we look at a conducting sphere. No, cylinder. We have a cylinder point, so we take a cylinder. Go tell it to your brother, young brother, or younger sister that is a cylinder. In a uniform electric field. Then we got to consider how this field will affect it. So consider the effect of placing a conducting cylinder, of radius A with its axis coincided with the z-axis. And by the way, it doesn't mean that the z-axis will always be up here. I can put my cylinder like this and still have this as my z. You get the point? So I can have radius this with its axis along the z-axis. The cylinder being infinitely long. If it is assume that in the absence of the cylinder, there is uniform electric field E is equal to E naught X.